Hello everybody, this is a screencast version of your lecture. So if you want to do quizzes and turning points, a bit more interaction, then you need to go to the lecture. This is just a screencast version, a little bit simpler, cut down, and you can use your pause button when you're watching it if you want to go through anything further in detail. So first let's look at the theory behind the method of sections. So it's similar to a method of joints in the sense that with the method of joints we're saying if we cut around a joint, that joint cannot move, assuming of course that we're dealing with a pin jointed framework. Well, method of sections is saying that we can cut through the framework, and when we cut through the framework, we kind of imagine that those frameworks are going to move slightly apart. Neither of those pieces of framework are moving. For that to be the case, there must be internal forces that are balancing the external forces. And we have come across that idea before with the method of joints. So we have these, in each member we imagine there to be an internal force, where we have an internal force pointing away from this joint here for this member, and at the other opposite end of the member, at the other joint, we imagine there's a force pointing in the opposite direction. These two forces need to be the same magnitude, and since they're pointing in the opposite direction to one another, they're going to cancel out. So they're not going to create any force in terms of the overall framework. There are only forces which are counterbalancing the external forces being applied. So let's consider me being squashed 10 newtons by someone, or rather someone's pushing me 10 newtons this way, and for me not to trip over, I would need someone else to push me 10 newtons in the other direction. Now if we cut me through the center, the internal force that I'm experiencing overall is going to be 10 newtons, because we're going to take half the body. And so we've got 10 newtons from the outside, the external force being applied, and so inside there must be this internal 10 newtons. Okay? Right, so let's come back to this problem that we're doing here. So we're cutting through the members. We pick up a cut where we're going to just cut through 3 members, and that's because we're going to use summing up the forces in the x direction, summing up the forces in the y direction, and we're going to take moments. So we're going to have 3 equations, which means we can deal with 3 unknowns. What I'm going to do is after I've made my cut through the framework, is I'm going to throw a bit of the framework away. And in this particular case, typically we throw the right hand side away. We don't have to throw the right hand side away, we could throw the left hand side away, but on the whole we throw the right hand side away. Now the members that we've cut through, we imagine they now magically become forces. Yeah, so these are now magically changed from being members to forces, and the forces need to be acting down the same direction as the member that you cut through it. And we're also going to imagine, for sake of argument, that the force is pointing away from the joint in each case. So the cut members are replaced with external forces from the thrown away piece of framework. So we've thrown away the piece of framework, and then we've made these members into forces. And these internal forces are the only things we're looking for. These forces need to still be here. These external forces still need to be here for our calculation, because we're doing this problem up here. We're cutting the body in half, and we're looking for the internal force. So go back to the diagram. What you want to do is you want to make your cut such that it's somewhere where it's a force you're interested in. Let's say we wanted to find out what EF was. Okay, so if we did method of joints, we'd probably start at this joint here. We would have to go on to joint B, because if we went on to joint E, there'd be 1, 2, 3 unknowns. If I go to joint B, there's only 2 unknowns. So I'd need to go to joint A, then to joint B, and then I could be in a position of going to joint E. Okay, so to find this the force inside this particular member, EF, I would have to go do 1, 2, 3 joints. So it can be a better method than using method of joints. Usually when you're looking for a member, the force inside a member, well away reaction points typically. Don't forget that we need to keep these external forces. Okay, they need to be there in our calculations. So there they are, everything's fine. We can take moments anywhere, but the usual place where you're going to take moments is going to be this point here, because it almost looks like a hinge where we have 2 forces coming out at that point. So if I take moments around that point there, that means the only only unknown force that creates a moment will be this BC term. So you see the advantage. So usually you go back and take your moment wherever these 2 unknowns coincide. So determine the unknown external forces, so external forces, so they're the internal forces I'm looking for, using a free-body diagram of the structure. Cut the framework into sections at the point where you want to find your particular member. Assume that the forces that you've created are all going to be in tension, i.e. pointing away from their joint. Resolve the forces in the X and the Y direction, and then you want to resolve the forces, you want to take moments. So we've solved these 3 terms. So we've solved the forces in the X direction, Y direction, and we've took moments. So let's actually do an example and see what this looks like. So here's my example. A nice framework. Can use 2 meter equilateral triangles, which means we end up with 60 degrees. And apply 12 newtons down here. So that means that the distance from here to here is going to be 1 meter. Okay. This is quite straightforward, I think, to be able to work out what that's going to be. So you can have 12 newtons times by 1. You could work out the reaction if you took a pivot here. So you've got 12 times by 1, and I don't know what this is in terms of its labeling. So let's call this reaction right hand side. So the reaction on the right hand side will be minus, what will be 4. So R right equals 0. So that gives me the reaction on the right hand side will be 12 divided by 4, so that will be 3 newtons. So you can see, you can very quickly solve this problem. We've got 3 newtons going up that side, and we've got 9 newtons, because 9 plus 3 equals 12 going on the left hand side. So working out the reactions for this problem is nice and easy. So there we go, we've labelled them up. We've got the 12 going down, the 9 on the left hand side, and the 3 going up on the right hand side. So the next thing I want to do is find the internal forces BC, BE and DE. Okay, when you get a question like that, do a little shading for the members they're saying. So they want DE, they want BE, so I want that one, and they want BC. Okay, so when you shaded them in a little bit, you can see where am I going to take my cut. I'm going to cut it through there, yeah? So we'll cut it through those 3 members, and then that will give us the members that we're looking for. Right, so there's the 3 forces that we've now created, and we're going to treat them as if they're external forces, but that's the exposed internal forces we've now got, okay? And these forces need to balance these external forces that we're keeping on the left hand side. So I'm going to call this force here DE, I'm going to call this force here BE, and I'm going to call this force here BC. And as I said, those 3 forces now need to give me terms that will then counterbalance, counteract these external forces. At this stage, you probably want to be doing a little bit of geometry, so you could maybe try and fit a triangle in and see what your geometry is looking like. So we know these are 2 meters, 2 meters, okay? So if I split a triangle in half, we've got 1 meter. If we go straight down, we've got 2 meters going along here, and going down here I'm going to use Pythagoras, so we're going to go what would that be, 2 squared plus the height squared plus 1 squared. So therefore we've got the height equals 4 take away 1 square root. So the height is going to be 3 square root 3 meters. So I've worked that out. That's 60 degrees. To swing, so swing through to go to the horizontal is 60 degrees. To swing through to go from this diagonal to the vertical is going to be 30 degrees. We're swinging half of 60. So you do your geometry, and then what I like to do is I like to avoid using signs. So I might do a little bit more geometry here. So I've got my 60 degrees there, and I'll do some complementary angles and work out that pointing straight up is 30 degrees, and then maybe work out what the height is there as well. So here I could work out that the hypotenuse plus what have we got? We got the hypotenuse, which is h, equals the height, so I'll call that little h squared, plus the length, call that l squared. So we don't know what the height is. The hypotenuse we know is going to be 2 squared plus h squared plus 1 squared. So we've previously seen that the result for that is √3 meters. The other stuff we want to look at, so we've done our lengths, and the other thing we could look at is our trig. So cos 60, what does cos 60 mean? Well, if I ever see cos 60 in my equation, I want to do the adjacent divided by the hypotenuse. So if I ever see a cos 60, I want to do 1 divided by 2. If I ever see cos 30, then I want to do the adjacent, so that's √3, divided by 2. So that's √3 divided by 2, so that's good. Right, so I think I've got everything now to tackle this problem. I can start looking at this BE thing, and I can start resolving it so that it's going to be split up into two components, one component pointing upwards and one component pointing along the horizontal. And that's what I've done here. So need to go back to my geometry of how I did that. So I have BE, whoops, not quite right, is it? So we've got 60 degrees here, 30 degrees here, and we've got BE going down here. So if I want to split it up going along the horizontal, I want to say BE times cos 60 is going along this horizontal. So we've got plus BE times cos 60. And if we want to resolve BE going straight up, then that will becomes BE times cos 30. So going straight up, it will be BE times cos 30. Okay, so I can get rid of this and replace it with these two components. And that's what we've done here. So here we had, remember, it was BE cos 30, and here we had BE cos 60. And what you want to do is go back to where you've been working out your trig, and you worked out that cos 60 is going to be a half. Cos 30, the smaller angle, it will be √3 over 2. So here we've got the angle where we've swung through 30 degrees. We've got the √3 over 2 times by BE. And for the larger one, we've got a smaller number, we've got half BE going in that direction. Okay, so what do we want to do next? Well, we've got two options really. We could either take moments about this point B, or we could resolve in the y direction. And why are those two possibilities? If you take moments about point B, then you're going to get rid of these unknowns, and the only unknown that you'll have will be the DE. If you resolve in the y direction, the only thing that's pointing in the y direction that's unknown is the BE. So you've got a choice. Ian decided to take moments at B. Okay, so let's do that. So if we're going to take moments at B, we're going to need to know a little bit more about the geometry to work out what my moments are going to be. So I go back to my geometry sketch and work out where things are going to be in terms of the moments. So I know that this height from here to here is going to be √3 meters, and I know this distance, for example, from here to here is going to be 1 meter, and I know this distance from here to here is going to be 2 meters. Okay, so does that give me enough information now to start taking moments around this point. I think it does. So there I have imposed my distances. So what I'm going to do is we are going to take this DE force, and we're going to imagine that it comes to this just above the pivot, so it hits that line there, and then we measure its distance. So the distance to get from here back down to the pivot is √3 meters. This 12 away in this odd position up here, we're going to bring it down, and we're going to imagine that the 12 hits here, and then we'll measure the distance from the pivot as it hits the x-axis. This one here is already on the x-axis. That's an easy one to do. So just getting rid of this framework, okay, and now looking at the moments that we've got DE times by √3, and that's going to be a positive moment. Then we've got 12 times by 1, and that will be a negative moment. And then we've got 9 times by 2, which will be a positive moment. So we can see we've kind of imagined that 12 to drop down to this point here, the DE maybe to shift across a little bit to the right. So it's straightforward to do our moments. What result did we get? Sorry. So the result will be, let's start with the DE. So we've got √3 times DE. So that's a positive moment. Take away 12 times 1. Okay. Because that's negative, so we're going around this way, so that's positive. And then coming around this way on the other side of the clock face, that's negative. So the clock face is going up here, and this arrow is going up here. So so that's going to be a positive moment. So we've got 9 times by 2. So what does that give me? Minus 12 plus 18. Whew. Overall, I make that to be 6. So that will be a minus 6 on that side. DE divided by √3. Don't like √3's on the bottom, so times top and bottom by √3, and that gives me minus 6 times by √3. √3 times √3 becomes 3. You can see I've now got 6 divided by 3, so that's going to become minus 2 √3. Okay, let's grab my calculator, and that's going to be 2 times √3. So that gives me a value of 3.64 newtons. Okie dokie. Okay, so I think I must have skipped a step. Yeah, I didn't resolve in the y direction here. So I should have done this step at the beginning. Sorry, I skipped this one. So the first thing I did was resolve in the y direction. So √3 divided by 2 times BE. So that's going to go upwards in the y direction. Plus 9. That's going up. Take away 12. Equals 0. So we've got what? √3 divided by 2 times BE equals 3. BE equals 6 divided by √3. I don't like √3's in the bottom, so that's going to be 6 √3 divided by 3, which ends up as 2 root 3. So that is going to be 2 root 3. Okay. Okay, then do this calculation. Let's just check everything's okay. So DE times that should be a minus, and yeah, I've made a mistake there, minus. So that's in compression. So you see how easy it is to make a mistake. Forget your minus sign. And here we end up the same result, 3.464 newtons, and that's in tension. Okay. Right, so the final thing is we're going to resolve the forces in the x direction. Okay, so in this case you see that we're going to have DE plus BC plus half BE equals 0. And I worked out what DE was, and I've worked out what BE was from my previous attempts. So previously I found that BE was 3.46 and DE was minus 3.46. So I'm going to substitute that into the summation of the forces in the x direction. So that's the DE plus the BC plus half BE. Substitute my numbers in, keeping the minus sign there and making sure I don't have one there. That ends up as being half 3.56, which ends up as a solution of 1.73 newtons tension. Okay. And what I can do finally is I can compare it to a computer simulation and check my answers. So these were the values I was looking for. So we had two 3.46s, one of them in compression, one in tension, and the final number, which was half the value in tension. So I've made videos for you, which you can go on Blackboard to follow further. There's this is an example that I made up myself. Okay, so you can only really solve this through method of sections, so it's going to take you a while. And then there's some examples in the book, and there will be videos of these examples that you can then follow from the course notes. So that's the videos for page 41 and page 44. Okie dokie, that's it.